at the Mides of March 3:15, and we're going to talk about Windows and do an SEH-based exploit tonight. So let's start with the slides. All right. And I see, good evening, Yuri. All right. So, all right. So we're going to talk about the thread environment block and the process environment block, buffer overflows, ASLR, the frame-based exception handlers, and SEH handlers. So this is pretty dense technical stuff, and you don't really have to understand it in much detail to do the projects. You'll see some of it in the projects, but a lot of this is technical stuff we won't refer to directly. A Russian Forex scam, but the address is Traitly-Sachs. More later. Yeah, well, I'm not sure what you're saying there. Anyway, so, all right. So the thread environment block is a region of memory that stores information about the executing thread. And so this was officially undocumented, partially documented by later versions of Windows. And what turned out is so many programs use undocumented thread environment block fields that they're effectively part of the API. This is something you see, especially in the malware analysis class, we talk about this. You can't hide anything about Windows from the user. If you use a powerful debugger like WinDebug, you can get the assembly code for every part of the kernel, and you can see the data structures, so you can figure out what they do. And so Microsoft has a bunch of things they wanted to reserve for only internal use, but other people figured them out. And so a lot of people are using things that were not really intended for public use. And the thread environment block is one of them. It gives you a lot of information. It shows the error, the import address table, the startup arguments, and many other things. So among the other things that's on there is the SEH handler. There's a pointer to the SEH in the thread information block, also called the thread environment block. So we talked before about the structured exception handler, and that's what we're going to attack in tonight's project. So there are registers in the processor. In addition to EAX and EBX and ESP and EBP, there are frame registers, segment registers, FS and GS, and they are not used by very much anymore, but on Windows 32-bit, FS is used to point to the thread environment block. So that's one way to find out where it is. And so the process environment block is an opaque structure as opposed separate from the thread environment structure, and it's only supposed to be used internally by Microsoft. And only a few fields are documented. I don't think anybody's using this directly very much, but there is a process environment block. Here's things like whether it's being debugged, the base address of kernel 32 and ntdil, some parameters and session ID and so on. So there's some things people have figured out here. All right. So those are data structures that help you find out what's going on in the threads and processes on a Windows system. So now, when you do a buffer overflow, we've done plenty of these, you know how it works. The classic buffer overflow gives you control of the instruction pointer. So you'll have a variable like a name, then you exceed 20 characters and write stuff. So you write a bunch of stuff, and eventually you write a special point at the end of the frame, which is the return pointer. So this gives you control of the extended instruction pointer. So one way to do it, if you have enough room, is you put your attack in here, you put in a NOP sled, and then you put in the egg, which is the code you're trying to execute, which you're getting from MSF Venom mostly, and then you put padding here to reach there, so you make the EIP point back to the NOP sled, and now you can take over the box. Now this is the classic buffer overflow, but it means you must be able to overflow the buffer, you must be able to overflow the end of it and hit the return value, you must be able to find where you are in memory so you know what value to put here, and you must be able to execute code on the stack so the code you injected there will run. And that's why all these modern defenses are there to stop many aspects of that. Now, the alternative is to overwrite the structured exception handler. Now, when there is an exception, like a divide by zero or some illegal instruction, it raises an exception, the code stops processing in order, and it jumps to the exception handler, where it tries to see if there is code there to handle this unusual situation. And if you overwrite the code, the pointers in the SEH, you can now redirect code there. That goes into the EIP. So it's another place you can go to point back onto the code you've injected. So that's what you do here. The structured exception handler is also down here in memory. So you overflow with data until you hit the exception registration, and now you cause an exception, and the exception causes you to jump back into your code. That's just another way to do the same thing. All right, so let's talk about ASLR. This redistributes things. So without an ASLR, you just use the lowest available memory. So Windows starts, then your antivirus, then IS, then SQL Server, and whatever else you're running. And it's pretty much in the same reproducible location every time you restart the machine. And you can rebuild the machine with the same software on it and get a pretty good idea where it is. But now that all versions of Windows have ASLR, it just randomly chooses a memory location for every program every time you restart it. And so you won't have any idea where you are. And when you do your exploits, you cannot find the absolute addresses of anything. So what you do is ESP points to the top of the stack frame. So when you're inside the function, you can often have a jump ESP, and at the point of the crash, the ESP will point to some of the code you've injected, so you can put a return value that points to a jump ESP, which takes you back up here, and that's a trampoline attack. It only works if you can find a jump ESP that doesn't move. So you have to find some Windows module that does not have ASLR turned on, and there are a few, and then find a jump ESP in there and go there. That's the simplest case of return-oriented programming, a trampoline, where you use one instruction elsewhere. All right, now if you wanted to get to the structured exception handler, it's also randomized so you can't find it. You used to be able to find the address in EBX whenever there was an exception, so that made it pretty easy, but Microsoft cleared the registers now to stop that. But when you have an exception, the address is at ESP+8. So if you can find pop return, that will take you to the structured exception handler. So it's another way to find something, even when you have address space layout randomization, so it has a variable address. And we're going to use some techniques like that in tonight's project. All right, so here's why the exception handler works. If you have some kind of illegal instruction, then it calls the exception handler, and it sets a series of stack frames, and it has to test them. So it goes to the thread environment block, has the address of the first exception handler record, and when an exception occurs, it goes through the list. Here's the first exception handler, here's the next, here's the next. So you have a series of possible exception handlers, and it tries them all to see if the developer of the software has written code to handle this exception, and if the developer has not, then it defaults to the operating system, which will raise some generic message like this program has crashed. All right, and so here's what the code might be. You take the exception handler. This is just going to return. So here's code that would cause an exception where it sets EAX to 0, assembly code, and then calls it. So it tries to start a function at location 0, which is not legal. That's a kernel address. And so then it will cause an exception, and you'll run the exception handler. All this does is exit, but normally you would write code here that does something like display a message to the user or something like that if you have an exception. So you can view SEH chain in immunity, and it will just show you the addresses. Here's the addresses of the handle. These are the system address exception handlers, part of NT-DIL. So it tries this one, tries that one, tries that one. And if you go look at follow the address in stack, you'll see the structure of it. Here's a pointer to a record. Here's some stuff about the handler. Here's a return. And here's a pointer to the next SEH record. And here's the handler. So there's a series of addresses with code in them there. All right, so if you overflow the stack, this is another issue we've seen before. In our buffer overflows, we would overflow the stack on Linux and redirect code, and then it would crash afterwards because we had collateral damage. We didn't fix the stored EBP, and you often hurt other things when overflowing the stack. You hit various variables. So it's really quite common that after you do a buffer overflow, you cause an exception because you damage other variables. So if you want to gain control of the exception handling, there's EBX, and on later versions, you can, it may be hard to find the exception registration record. So the old Windows process was use EBX, put a jump EBX to get into the exception handler. And the new Windows process is the third value down contains the pointer to the exception handler, so you do pop return to get there. And we'll use this pop return technique later. All right, now there are a bunch of defenses. Microsoft put in a bunch of defenses starting with Vista to stop buffer overflow attacks, like non-executable stack and address space layout randomization. And now they put in a bunch of SEH protections in modern versions of Windows. So Windows 2003 server had some defenses. Before it would run the exception handler, it would check things. The handler is not allowed to be on the stack. If it's in a loaded exe or dill, it might be accepted, but anything else, it would test. If it's not, then it would take it. If it was marked as not allowed, that would stop it. And if it had a no load configuration directory, or one with a small size, then it would call it valid. So these were some tests to pick up really bogus exception handlers. But there were ways to do it. You could use an existing handler, put it in code outside all modules, or so on. There were tricks to get around it in 2003, but that's so out of date, this is not that exciting. What's more interesting is the Windows 2008 defenses. And these are the ones we're going to deal with in the project. So a normal SEH attack goes like this. Here's an intact exception handler. So it goes here, has one handler, then another handler, then another handler, and then it gives up. This is the list of what you do is you overwrite this with an address going to like pop return, and then it will come back to this code. So you cause an exception, it will do pop return, which will jump back here to the code you're able to inject. So if you're able to inject into the exception handler, you can put an address here that points to a pop return that doesn't move, and then you can put your exploit here, and you'll be able to execute it with an exception. So that's the normal SEH attack. So Microsoft wants to prevent this. So
the two addresses not the same.
What's that?
The two addresses not the same.
The two what?
Two addresses not the same on the right side.
That's right. The addresses. This one here. Yeah. See, an exception will cause this exception handler to be run, and this it'll go to the exception handler, which is randomly located in memory, but the data you put there is this, and this points is this address. This is some module that doesn't move that has a pop return.
What is the one below that address? What is that address used for?
This stuff down here.
No, the one that when you open up on the left side.
This one here. Oh, this is the code. This is not an address. I don't think this is an address. I think this is code, but I'm not sure. This is either an address, your code, or the real code that runs your exploit. Yeah. Good. Thank you. All right. And so Safe SEH is a compiler switch in Visual Studio 2003. This is quite strong. This will list in the code what allowed addresses are possible for the exception handler and not let you change them. This is quite strong, but it's only going to work if you compile it with this switch turned on, so legacy code written before Microsoft produced this will remain vulnerable. SE hop is one that will verify that the handler is intact before using it. And so the text, it goes hopping through the SEH chain, checks the first one, points to the next one, points to the next one, and points to a correct endmark. This is very much like Cisco's check heaps defense. So it means if sloppy exploit that overwrites the exception handler and doesn't carefully repair the rest of it will get caught. So this is an issue. And so it goes like this. An exception registration record has a pointer to the next one and then the handler. So your handler is here doing something and they're pointing to the next one. And so, all right. And if it can't hop to the end, then SE hop will bust you. So that's how SE hop works. It adds an extra record at the end of the list. It walks to the end and makes sure it can get to the end. So it'll detect if any of the next pointers are corrupted, breaking the chain. So you'll see it here. Valid SEH chain goes to various things like this. An invalid SEH chain has been overwritten and it doesn't have a valid next hop that goes somewhere else here. So that's what you get with the sloppy overflow. All right, so it's enabled by default in Windows Server 2008 and later versions on the server. It's, however, it's disabled on client machines, but you can enable it in the registry. This is true of a lot of the more complicated defenses. They're only on servers because there's a lot of games and client software people want to run that don't survive these rules. So Microsoft lets you run it on clients, but on servers they don't. All right, and so you can control it, however, in the registry, NT current version image file execution options. You choose the program, and program by program, you can choose whether to disable exception chain validation in the registry. So you can tell it whether you want to allow this defense to operate on the code. So you could go turn it off to let your legacy code run that can't handle this defense. And so if you do have it turned on, and then you trigger an exception, it'll tell you the program is unable to process the exception. Just like if you have a stack cookie and you overflow the exploit, it'll stop and say stack smashing detected, or a variable like that. And we'll see this in the project. You're going to get this if you forget to turn off SE hop. You won't be able to do the project we're going to do tonight. So let's take a look at a Kahoot, which is 8A, which is here. That's what I thought. Seemed a little quiet. Give it a few more seconds. All right, I guess that's it. Oh, maybe not. Okay. All right. All right, so what defense is enabled in servers but disabled in clients? SE hop is the one enabled on server versions of Windows, but it checks the integrity of the structured exception handler chain. It's enabled on servers but disabled on clients versions of Windows. All right, which defense cannot protect legacy code? Safe SEH is the one you have to compile the code with this switch, so you'd have to recompile legacy code from source to add this protection in. All right, which method only works on old machines before XP, Service Pack 1? Jump EDX would take you to the structured exception handler on old versions of Windows, but not anymore because Microsoft wised up and clears all the registers when you have an exception, so there's no data in them leaking into the exception handling process. All right, which method finds the SEH in modern Windows version? hit return, we'll still find it. All right, and which one is a register pointing to the thread environment block? Yep, that's FS, one of the segment registers, not used for much these days, but it does have that property. All right, that's faces, the no, that's opcode, I don't know who that is. You have it, know who that is. All right, so, let me turn off the recording.